everyone. Today we're diving into the intriguing world of Persian paradoxes, which reveal the complexities behind what seems like a straightforward process. Just as we strive to distribute tasks fairly in our group, apportionment deals with distributing seats in a legislative body based on population. Imagine if we allocated more resources to our project, but one of us ended up with fewer resources. This mirrors the Alabama paradox, where increasing the total number of seats causes a state to lose one. Similarly, the population paradox occurs when a faster growing state loses a seat to a slower growing state, like someone efficient in our group getting fewer tasks. The new state paradox shows how adding a new state can reduce seats for existing states, akin to a new member disrupting our task distribution. These paradoxes highlight the challenges in creating a fair apportionment system and emphasize the importance of addressing them to ensure equitable representation. As we explore these, we'll understand the complexities of political representation and the quest for fairness, just as we seek balance in our group.
And here's apportionment paradoxes to report about description. Paradox in apportionment occur when the method used to distribute resources or representation among groups lead to counterintuitive and seemingly logical outcomes. These paradoxes are especially prevalent in contexts such as political representation, budgeting, and broadcasting. For example, the population paradox reveals how a group's share can decrease even as its size increases, contradicting the expectation that a larger group should receive a larger portion. The Alabama paradox shows that adding more resources can cause a redistribution that results in some groups receiving less than before. These paradoxes highlight the challenges of creating fair and consistent appointment system, where attempts to balance opportunity and equity can lead to unexpected and contradictory results. And understanding and addresses these paradoxes is crucial for developing allocation methods that are both just logical. Thank you.
Good day, listeners. Today, we're diving into a fascinating world of apportionment, specifically focusing on paradoxes and the terms you need to understand. Apportionment is the process of distributing seats or resources often used in the context of political representation. It sounds simple, but the way these seats are distributed can lead to some strange and unexpected outcomes, which we call paradoxes. Let's break down a few key terms that will help you navigate these paradoxes. First is the apportionment method. This is the mathematical approach used to allocate seats. Common method includes Hamilton's method, Jefferson's method, and Webster's method. Each has its own way of dealing with fractions and dividing up seats. Next is the quota rule. According to this rule, the number of seats a group receives should either be its lower quota or its upper quota. If an apportionment method violates this rule, it can lead to paradoxes. Third is the population paradox. This occurs when a state or group gains population but loses a seat, while another group with a smaller population growth gains a seat. It's counterintuitive, but it can happen. Next is the Alabama paradox. Here's a real head scratcher. This paradox occurs when increasing the total number of available seats results in a state losing a seat. This was discovered in the United States during the 1880 census, hence the name. Fifth is the new states paradox. This happens when adding a new state or group causes a shift in the seat distribution that affects existing states. Even though the population sizes haven't changed, it's like musical chair but with Congress seats. In conclusion, these paradoxes shows that while we strive for fairness in representation, mathematics can sometimes produce unexpected and seemingly unfair results. Understanding these terms helps us navigate the complexities of apportionment. That's it for today's lesson. Stay tuned for more intriguing insights into the world of mathematics.
The population paradox is a counterintuitive result of some procedures for apportionment. When two states have populations increasing at different rates, a small state with rapid growth can lose a legislative seat to a big state with slower growth. This means that even though the smaller state has a rapid growth, the distribution of seats will favor a larger state because seats are distributed based on overall population. So for example, we have here, a small country has 24 seats in a Congress, divided among the states according to their respective populations. The table below shows populations after a 2000 and 2010 census. First, you need to get the divisor. To get the divisor, you need to divide the sum of the population of all districts by the number of seats. So the total number of districts is 37,600 divided by 24, which is the number of seats, is equals to 1,566.67. Now we have the divisor. We may proceed on finding the quotas of the districts. So to get the quota, we must divide the population of the district by the divisor. So District A has a population of 5,300 divided by the divisor, which is 1,566.667. We have a quota of 3.383. And so on. So District B has a quota of 6.319. District C has a quota of 14.298 with a total of 24. Next, to find the initial value or the lower quota, we just take the quota and remove the decimals. So the quota is for District A is 3.383. So the initial value is 3. We just remove the decimal. Same goes to District B and District C with an initial of 6 and District C with an initial of 14 with a total of 23. Now notice that the total is 23. So the extra seat will be given to the district whose quota has the largest decimal. So here we focus on the quota and notice that District A has the largest decimal. So we just add the extra seat to that quota district. Now we have the final apportionment of each district with a total of 24 seats. Let's proceed to the population of the 2010 census. So the divisor is 108.75. Same solutions with the table above. Now, notice that District A in 2000 has 4 seats and District B has 6 seats and District C has 14 seats. While in the 2010 census, District A lost 1 seat, District B gained 1 seat, and District C remained with 14 seats. So comparing the two tables, notice how District A, who has the largest population growth with 28%, received 4 seats in 2000 but only 3 seats in 2010. It's because the distribution of seats are based on overall population. So, bisan pagun sa kadako ang growth ng district, if gamay yung population, then makuhaan jud siya og seats sa final. Now let's proceed. The new state paradox. So if a new state is added as well as a proportional number of new seats, it seems logical that the number of seats of existing states would not change. However, this is not always the case. Adding a new state with its fair share of seats can affect the number of seats apportioned to other states. When a state gains or loses a seat in this situation, this is called the new state paradox. So, suppose a certain city has two districts, which is District A and District B. The populations of the districts are given in the table. There are 100 police officers that are employed to patrol these two districts. So, of course, to get the divisor, we just divide the total with the number of police officers. So we get 100,000 divided by 100 is equals to 1,000. So that is our divisor. Now, suppose the city expands to cover a new district called District C. As a result, the city hires 5 more police officers to cover the new district. Bring the total to 105 officers. Now, the total population of the city is as shown in the table. So the divisor is 1022.381. Same solution with the other divisors, which is the total is 105,250 divided by 105 officers. Now, of course, to get the quota, we need to divide the population of districts with the divisor. So 10,450 divided by 1022.381, District A got a total of quota of 10.43. District B has 89.34 and District C has 5.24. To get the initial, we just get the quota value and remove the decimals. So District A has 10, District B has 89, and District C has 5. Now notice that the total values of initial is 104. So the extra seat goes to the district whose quota value has the highest decimal value. Here, District A has a highest decimal value of quota with 10.43. So the extra seat will go to District A. So the final values are District A has 11 officers, District B has 89 officers, and District C has 5 officers with a total of 105 officers. The addition of a new district and a corresponding increase in available officers will cause a change in the apportionment of other districts. District B lost an officer, and District B has a new officer. Then, the new state paradox occurred.
Stumble problem of new state paradox. Suppose a certain city has 2 districts, A and B. The populations of the districts are given in the table. There are 100 police officers that are employed to patrol these 2 districts. Apportion the officers using Hamilton's method. Suppose the city expands to cover a new district called District C. As a result, the city hires 5 new police officers to cover the new district. Bring the total to 105 officers. Now the total population of the city is as shown in the table. Steps and procedures. First, solve for the standard divisor. Second, determine the standard quota for each group by dividing its population by the standard divisor. Third, round each group's standard quota down to the nearest whole number. Fourth, sum the lower quota to find how many leftover seats exist. 5. Allocate the leftover seats
to the group with the largest decimal until no leftovers remain. The addition of a new district and a corresponding increase in available officers will cause a change in the apportionment of other districts. District B lost an officer. The new state paradox occurred.
Is the given in the first statement of the District A, District B, the population or the state of the problem. District A had 10,450 and District B had 89,550 and the total 100,000. So we need to find the quota initial and final. In order to find the quota, we need first to find the standard divisor. So the formula is total population plus number of seats. Total population divided by number of seats. Total population is 100,000 divided by the number of seats, which is 100 police officers. 100,000 divided by 100 is 1,000. Then we now have the standard divisor, which is 1,000. Now we can proceed to the solving of quota. First is District A quota. The formula is population of a particular group. Divided by standard divisor. Population of a particular group, which is the District A, is 10,450 divided by the standard divisor, which is 1,000, equals 10.45. Next is District B quota was 89,550 divided by standard divisor, which is 100, equals District A quota is 10.45, then 89,000. For the District B is 89,550 divided by 100 is for the next statement. The city spans and the same district, which is the district C. And with that, the city hires for the first statement, there are only 100 officers, and for the second statement, there is a the city hires 5 new police officers for the new district, which is C. So 100 police officers plus 5 for the new police officers. So for the second statement, now have 105 police officers. So just the same with the first statement, further to get about the initial and the final, we need to first. So the given of the district C is 5,215. So the total is 105,215. Now we need to find the standard divisor, which is total population Next one is round. Each group standard quota down to the nearest whole number. Will be added to the district. So the final is 10 plus
The interplay between paradox and apportionment and broadcasting illustrate the complexities and decision-making representation. Importance of ethical consideration in broadcasting. An apportionment method to mitigate paradox. Broader implication for policy making and public communication highlight the needed for transparent process to address the paradox effectively. ROKJ 1963, Social Choice and Individual Values, Balinsky M. and Laraki R. 2007, A Theory of Measuring Voting Power, Down A. 1957, An Economic Theory of Democracy, Bimber B. 2003, Information and American Democracy, Technology in the Evolution of Power, Political Power,